Throughout the years, humans have used animals for transportation, like horses for example, either for getting somewhere themselves or getting something someplace. But around the year 1886, the car was introduced and came to revolutionize the world. A car serves as a transportation method for more than one person at a time in a very fast manner. They come in different sizes and designs, some are electrical, others use gas, but overall they are very interesting machines for analyzing mechanical, electrical, and manufacturing aspects. Today, I will talk about two pieces that contribute in the functioning of the car. The first one is a car engine block. The engine block houses all the engine components like cylinders and pistons, which transfer combustion into mechanical energy, which drives the transmission and causes the movement of the car. As an example, BMW E36 contains the engine block M2031, weighing around 175 kilograms and made of nickel-coated aluminum. Here we can see a block diagram of the sand casting process. First we have a pattern, which is used to make the mold. The mold is made of zircon sand, usually mixed with a hardener and glue, to withstand the high temperatures of the molten metal. The metal can be an alloy. For example, we use aluminum alloy for engine blocks, which is poured into the mold. After the metal is poured into the mold, it is let to cool down and solidify. Then the sand is shaken out of the part, and the risers and gates used to transport the molten metal into the cavities are removed. Finally, the cassette part goes through heat treatment, cleaning the remaining sand, and finishing processes. After everything is done, there's an inspection to see any visual defects and to measure the part for dimensional tolerances. In the following image, we can see a cross-section view, a horizontal cross-section view of the mold used to cast an engine block, and also some of the cores that are used for this engine block. These cores allow the engine block to have hollow parts, which serve as passages to allow the air to flow through the engine as needed, and some will be for coolant to flow through, making sure the engine does not get too hot. The second part we'll be analyzing today is a piston. Inside of engine blocks, we can also find pistons, which have an up and down movement provided by a crankshaft, synchronized with the camshaft to let gasoline and oxygen inside the cylinders and produce a combustion with the compression caused by the piston and a spark provided by the plug. Pistons can be made by die casting. This process uses a permanent mold which allows repeatability and high precision, which is important to reduce friction between the pistons and the cylinder walls. In the next diagram, we can see the steps for die casting a piston. First, the die is prepared by heating. The molten material is poured. It is allowed to cool. The cassette part is submerged in hot water, then it goes through a heat treatment. The runner is removed. We had the pin boring, CNC turning, finishing process, grinding, reaming, pin fitting, and the final inspection. But why not use other manufacturing processes? When manufacturing a part, there is a lot to take into consideration. Some of these factors are size, weight, repeatability, cost, tolerances, defects, and the part material. For example, machining is a really bad idea for making engine blocks due to their sizes and weights. On the other hand, die casting is a good manufacturing process for making pistons, because these are fairly small pieces that need to be mass produced, so the high cost of the dies is justified because of the high production rate. Also, these parts need to have a good surface finish to minimize friction between the piston and the cylinder walls. And the sand casting process is ideal for engine blocks. Why? Because this casting process is good for small and big parts alike, not to mention that production costs are very low. And even though tolerances must be bigger for this manufacturing process, at the end of the cassette parts can go through a finishing process. But even after choosing a good manufacturing process, there still may be some defects in the parts casted, for example, shrinkage of the pieces. This is a defect that occurs because metals are less dense as liquids than solids, so when they solidify, they have less volume. So, how can we avoid this? Well, maybe by experimentation. The article Calculation of Shrinkage of Sand Cast Aluminum Alloys, published by the International Journal of Applied Engineering Research, made 8 experimental castings using different alloys, pouring temperatures, and mold coatings, as shown in the next table. Making a comparison between these experimental castings, shrinkage percentage can be estimated for future parts under similar conditions, and with this, we can know how much excess material must be included to compensate for the shrinkage. In the case of engine blocks made of aluminum alloy, the percentage of shrinkage is around 7%. Now let's talk about mass production. When making all these automobile parts, it's obvious that mass production is important. Almost everyone around the world uses this kind of transportation, so why not make multi-cavity molds to cast more engine blocks simultaneously? Well, at first it may sound as a good idea, but there are some complications with this. For example, engine blocks are pretty big pieces, so we will need to make a very big sand mold to cast multiple engine blocks at the same time. Also, all these engine blocks must be connected by a running system to allow the molten aluminum alloy to flow through the pouring basin onto all the cavities. The problem with this will be the time of solidification. If the molten metal solidifies before filling up all the cavities, there is a misrun defect. Not to mention that a bigger sand molds will be harder to handle by the robot arms at the foundry. However, there are still other ways to improve the production rate, for example, if we look at automatization of the plant. Going back to the solidification time of the part, there's a formula known as the Shibodinov rule, which is used to calculate the time the part will solidify, depending on the mold constant, the volume of the part, and the superficial area of the part. This is the formula. And then this is the formula for the mold constant, which depends on all this data: the melting or freezing temperature of the liquid in kelvins, initial temperature of the mold in kelvins, the superheat kelvins, latent heat of fusion, the thermal conductivity of the mold, density of the mold, specific heat of the mold, density of the metal, and specific heat of the metal. I tried to look for all this data and I found all these values. These are approximate values because the casted part is not pure aluminum, it's an aluminum alloy, and the mold is made of sand, but it's made of zircon sand, mixed with hardener and glue, not just regular sand. The error and the volume were proposed from a mechanical problem from a book, and the n is taken as a 2. With all these numbers, we get this mold constant. And after plugging it into the formula, we get that the cooling time for the solidified part will be 128 seconds approximately. But manufacturing is not just about the casting process or the mold design, it's about the materials. So what about plastics? Could we use plastics as a substitute for some part of the engine block or the pistons? Lighter parts can make cars faster, but this also contributes to fuel efficiency, because it takes less energy to move the car. That's why over the years manufacturing companies have used materials like steel, aluminum, titanium, etc. But could we use plastics? First, it may sound a little crazy because when we think of plastics we could think that they are weak. But as we have seen with alloys, we can mix materials to compensate for mechanical properties. The advantages of working with plastics is that they are lighter, cheaper, and easier to handle and customize in terms of color and branding than metals. An experimental engine developed by the Fraunhofer Project Group for New Drive System, NAS, proved that a fiber-reinforced composite material could be used to build a cylinder casing for one-cylinder research engine. Comparing it to its aluminum equivalent, the weight was reduced by 20%, while production costs stayed the same. However, they needed to overcome numerous technical challenges to achieve this. For example, the material needed to withstand extreme temperatures, high pressure, and vibrations without suffering damage. So researchers analyzed the engine design to identify the areas subject to high thermal and mechanical loads, and metal inserts were used in these parts to strengthen wear resistance. Another subject that is important when using materials is their biodegradation. Nowadays, polyethylene and polypropylene based plastic materials are being extensively used for commercial and household purposes, but these plastics are very resistant to biodegradation. The article Degradation Behavior of Natural Fiber Reinforced Polymer Matrix Composites makes an experimental setup by blending the PP, the polypropylene, with small additions of wood sawdust and wheat flour. Then the composite was exposed to various environmental conditions, to the open atmosphere, to moist soil, water, brine solution for a period of 15 weeks. And the results were very good. They revealed that the addition of both sawdust and wheat flour considerably improved the biodegradability of PP. In conclusion, plastics alone may not be strong or eco-friendly, but combining it with other materials, they can be harder and biodegradable, and a good substitute for a lot of metal components.